and see it. For the equation sheet, I think a good compromise, because there's so much material and a lot of equations, is for you all to be able to either have handwritten or typed equation sheets. So that includes, if you want to take screenshots of the equation sheet that I posted on Canvas, that's okay as well, and like arrange it on a Word document or whatever, so long as it's still within the page limit of the 2 pages back and front. So you can go through and kind of, if there are specific parts of it that you want to include, do that as well, and you can do a combination of writing your own and taking portions from the equation sheet. Okay, questions about that? Okay. Hopefully that clears up concerns with having enough space for your equations. And then the last thing, so today we're going to finish up talking about radiation. Hopefully we might spill a little bit into Friday. And then Friday we're going to do the course evaluation. And if there are any particular problems, practice problems that you want me to go over or topics that you want me to cover, please let me know by tomorrow so I can prepare that. And if not, I might talk about one additional topic that's pretty interesting, just how radiation affects color. We'll see if there's time for that, and depending on what you all want me to work on. Okay. Okay, so we started talking about on Monday relating these radiation expressions that we have for radiation exchange between 2 black body surfaces, and then our equation for radiation exchange between a small surface and much larger isothermal surroundings, kind of seeing how those equations are related and where they come from. And we introduced a couple more concepts to work towards that derivation. So the first concept was that radiation inside a cavity, an isothermal cavity composed of a single surface, approximates black body radiation. The second couple of concepts were that emission from real surfaces and absorption by real surfaces depends on the spectral and directional nature of the radiation. So basically we can write expressions for the emissivity as a function of the wavelength and direction, and the absorptivity as a function of the wavelength and direction. And then we use those concepts to develop Kirchhoff's law, which basically said if you have isothermal black body irradiation on some small surfaces in an enclosure, you can conclude that the emissivity is equal to the absorptivity. So we developed this under the pretty restrictive conditions that the surface irradiation corresponds to emission from a black body at the same temperature as the surface. And then we repeated that for the spectral emissivity and absorptivity and said we can show that's true for these same restrictive conditions, but we can also show it's true for some less restrictive conditions. And then we said, okay, the spectral directional emissivity and absorptivity are always equal to each other. And then we started working through under what conditions we could say that the spectral emissivity and absorptivity were equal to each other, and then the total emissivity and absorptivity. So we got through, so we're introducing the gray surface, and we got through basically stating that we can say these two quantities are equal if the irradiation or the surface is diffuse. And we showed how that was true by writing out the integral forms of these quantities here. So basically now we've shown the spectral emissivity and absorptivity are equal if the irradiation is diffuse or the surface is diffuse. And we're going to finish developing this concept of the gray surface and show how we can state when the total emissivity and absorptivity are equal. So that's where we'll start today. Okay, so we're going to go ahead and assume diffuse irradiation or a diffuse surface, so the spectral emissivities and absorptivities are equal. And we're trying to figure out under what additional conditions does the total emissivity equal the total absorptivity. So again, we can write out the integral expressions for both of these quantities. And there are two conditions that would make these quantities equal. And this is given that the spectral emissivity and absorptivities are equal. So first is just our original restrictive condition that the irradiation corresponds to emission from a black body at the surface temperature. So for this condition, we would be able to say that if it's emission from a black body, the irradiation, the spectral and total irradiation, is just going to be equal to emission from a black body. And so you can just look at the integrals and say, okay, we know these two quantities are equal. So then if this one equals this one and this one equals this one, then they're just identical integrals. But that's not a very helpful condition because it's the same restrictive condition that we started with. So the second condition that would make this true, if we say the surface is gray, and that means that the spectral emissivities and absorptivities are independent of the wavelength. So similar to the diffuse condition where it's independent of direction, here it's independent of wavelength. And so looking at the integrals, if these quantities are independent of wavelength, then they're constants with respect to integration over the wavelength. So you can bring them in front of the integral, and then they are equal to each other, so they cancel. And then you're left with the integral of the spectral emissivity over all wavelengths, which just integrates up to the total emissivity, or total emissive power, rather. So that would cancel to 1, and then same thing with the irradiation. This would just integrate up to G, and that would cancel to 1 as well. So now we're able to say if a surface is diffuse and gray, the spectral emissivity is equal to the spectral absorptivity, and the total emissivity and absorptivities are equal. And this is really useful because it's a much more commonly encountered engineering situation than blackbody radiation exchange. So a lot of surfaces you can at least approximate as being diffuse and gray. So again, for diffuse radiation, there's no preference in direction, so the emission has the same, the emission or irradiation has the same magnitude in all of the directions. And for a gray surface, that's true for over all of the wavelengths. Okay, so we have kind of all of the concepts now that we need to start developing expressions for the radiation exchange between diffuse gray surfaces. So we talked about radiation in an isothermal cavity approximates blackbody radiation, and we said for diffuse gray surfaces, the emissivity equals the absorptivity. So now let's put these together and talk about radiation exchange between these types of surfaces. And we're specifically going to talk about within an enclosure. So opaque, diffuse, gray surfaces. In an enclosure. So we're going to start by talking about an enclosure composed of multiple distinct surfaces. So now instead of having one isothermal surface, we're going to have multiple distinct surfaces that are individually isothermal, but the temperatures between the surfaces can vary. And then each surface is going to have some radiosity leaving the surface, some incident irradiation, and then it's going to have some net radiation exchange with the rest of the surfaces in the enclosure. So this is an important distinction, or we need to make an important distinction between this type of enclosure and the enclosure we considered previously, where we had just one surface that was all at the same temperature. So here the surfaces are individually isothermal, so that means that each surface temperature remains constant in space and time within that surface. But because they're at different temperatures, there's going to be radiation exchange between all of the surfaces. So if you just let the enclosure sit there, it would come to thermal equilibrium and all of the surfaces would eventually come to the same temperature. But we're going to assume that there's some sort of external input or output of heat transfer that is keeping these surfaces at different temperatures in space and time. And this is not as unrealistic of a situation as it might initially seem. So you could consider a room that has several different windows, and the windows are going to be at a given temperature if the outside is at much colder temperature than the room, and the walls are going to be at a different temperature depending on the temperature in the room, and also maybe one wall is adjacent to a room that is much colder than the other wall, and the floor is typically much colder than the walls and the rest of the room, unless you have radiant heating, for example, in which case it can be warmer. So it's not that unrealistic of a situation to have these different surfaces in an enclosure that are at distinct temperatures and that they're kind of maintained at those distinct temperatures. Okay, so the key difference between this enclosure and an isothermal enclosure that's just one surface is these surfaces cannot be approximated as black bodies. And that's because each individual surface will not necessarily absorb all of the radiation. So the reason that we were able to say an isothermal enclosure composed of one surface approximated a black body was because that surface absorbed all incident radiation because it was like reflecting off of all the surfaces and eventually getting absorbed. And it was the same surface. And so then to maintain a single temperature, it had to emit the maximum possible radiation. But for each individual surface, that one surface is not necessarily going to absorb all of the radiation in the enclosure because some will be absorbed by the other surfaces. And so therefore, it cannot emit the maximum possible amount of radiation. So individually, when the surfaces are at different temperatures and are distinct, they do not approximate black body behavior. Does that make sense? Any questions? Okay. It's an important distinction for developing the theory later on. Okay, so we'll say the surfaces are individually isothermal. And do not necessarily approximate black body behavior. Okay, the surfaces are at different temperatures. And they have uniform radiosity and irradiation. So that just means that the radiosity, for example, it could still vary with direction and wavelength, but it just means that every point on the surface will have the same characteristics. So it'll have the same kind of spectra and directional radiation emitted from it. Okay, so that's the difference between uniform versus diffuse or gray. But we're talking about specifically opaque diffuse gray surfaces. So some additional characteristics are transmissivity is equal to 0. The emissivity, absorptivity, and reflectivity are independent of wavelength. And independent of direction. So the total emissivity equals the total absorptivity. So those are kind of the properties that we're working with. And finally, we'll assume the medium is non-participating. So it's either a vacuum or most gases approximate non-participating behavior. And typically, for this type of problem, given the temperature of a surface, we want to calculate the radiation exchange. Or vice versa. Okay, so that's kind of the setup of the problem. We have an enclosure with distinct surfaces that are at different temperatures, and we want to calculate the radiation exchange between them. So we'll first focus on just one surface and derive some equations for the net radiation exchange at a single surface. So considering a single surface, the net radiation exchange at that surface is going to be what's leaving the surface versus what's coming into the surface. And so the total radiation leaving the surface is the radiosity, and what's coming in is the irradiation. So we're going to end up with several different expressions for Q sub I. So I'm just going to kind of label them as the more important equations for Q sub I. And again, you can think of this net radiation exchange as the amount of heat that would have to be either gained or lost by an external source for that surface to maintain its constant temperature, since there is net radiation exchange within the enclosure. So for an opaque surface, we know the radiosity is just equal to the emission plus the reflection, since there is no transmission. And again, the subscript I is just indicating that we're talking about this specific surface I. So now if we plug that in to our first equation, and we can rewrite the total irradiation which for an opaque surface is just the reflectivity and the absorptivity. Okay, so that's our second expression. a third equivalent expression uses the definition of the emissive power of a real surface. So that's the emissivity times the emissive power of a black body. And then given that definition, we can rewrite our expression for the radiosity. And then for the opaque diffuse gray surface that we're considering, this reflectivity for an opaque surface is going to be 1 minus the absorptivity. Since there's no transmissivity, reflectivity and absorptivity just equal 1. And then given our assumptions, we're able to say that that is equal to 1 minus the emissivity, since these two quantities are equal. Okay, so now given both of these, we'll rewrite our expression for radiosity. So now we're working only in terms of the emissivity of the surface, and then the emissive power of the black body, which is pretty easy to calculate, and then the irradiation. So most of these things are going to be fairly easily known. And we're actually going to solve this for the irradiation. So now that's in terms of these other quantities and the radiosity. And then finally, we can plug that into our initial equation up here, the radiosity minus the irradiation, and do some rearranging. And we're left with this expression. So third expression for Q sub I. And the reason that we've written it in this way is because we're going to represent radiation exchange using a circuit again, so go back to the circuit concept. And so we're writing this in the form of a driving potential divided by the resistance. So for the previous expressions for thermal resistance, we had the overall temperature difference, T1 minus T2, the total temperature difference of the system we are considering, and that was the driving potential, right? That's what causes heat transfer, is the temperature difference, and then divided by the total thermal resistance. So we're casting this in the same way, where we have the driving potential in the numerator and then the thermal resistance in the denominator. The potential for this this equation isn't quite as intuitive, but you can kind of think of it as, so if the emissive power that the surface would have if it were a black body exceeds its radiosity, then this quantity will be positive, which means there's net heat transfer from the surface. Whereas if it does not exceed the radiosity, then it's net heat transfer to the surface. So it's not quite as intuitive because you're talking about both of them are properties of the surface, but basically the way it works out and just from the derivation, this is kind of what you get as far as the radiation heat fluxes. So that's what's driving the heat transfer. Okay. So this is pretty interesting actually, because we can look at this equation and say, let's say we have a special case where one surface is much larger than the others. And so both intuitively thinking about it and looking at the math, we can show that we're just going to go back to the situation where we have basically black body radiation exchange in a cavity. So if you say one surface is much larger than the others, that's the condition of the area of that surface going to infinity, which has the same effect mathematically as the emissivity going to 1. So basically forcing this term to 0, forcing the resistance to 0. And if you just think about it, if one of the surfaces is much, much larger than the rest of the surfaces, there's a high probability that it will intercept all of the reflections of the radiation within the enclosure, and therefore absorb almost all of the radiation and behave just like our previous situation where we had just one isothermal surface for the enclosure. So you can show that this expression is just a generalization of that behavior for multiple surfaces. So we can say this much larger surface approximates black body behavior. Okay, does that kind of make sense how we started with a more general case of a bunch of different surfaces and then said, for this special case, we can kind of get back to that isothermal enclosure. Okay, so a little more generally, we'll talk about radiation exchange between the surfaces. So basically, we've developed several different expressions for the radiation leaving this surface I. And this last expression, most of these quantities will be known. We can calculate the emissive power of a black body and the emissivity of a surface. And the last thing is we need to be able to calculate the radiosity. And we'll do that by considering the radiation exchange between all of the surfaces. So our goal is to calculate the heat transfer at a surface, and the last thing we need to do that is we need a way to calculate the radiosity. And the reason we consider the radiation exchange between all of the surfaces is for basically for one surface, you know that the irradiation on that surface is equal to the radiosity from, or the sum of the radiosity from all of the other surfaces that impacts that one surface. So we can relate this irradiation from each of the different surfaces to the radiosity. So I'll write this down and hopefully it'll make a little more sense. So in terms of the view factor, right, because only a portion of the radiation leaving a surface J is going to be incident on or absorbed by a surface I. So we're relating the irradiation on this surface I times its area And that's going to be the sum of the radiosity from all of the surfaces over their areas multiplied by the view factor between them. So how much of the radiation from J is incident upon I, which is what the view factor means written in this way. And we know that Aj times Fji is equal to Ai times Fij. So we can rewrite this. And now the summation is over J, and the area of the surface I is going to be a constant independent of that summation. So it'll cancel. And we have this expression for the irradiation in terms of the view factor and the radiosity of the other surfaces. And we're going to bring our original expression for the radiation exchange, Q sub I, back. So everything that's leaving the surface minus everything that's incident upon the surface. And then plug the expression, our new expression for the irradiation in. And we can use the summation rule to rewrite this. So we know the sum of the view factors for all the surfaces in an enclosure are equal to 1. So we can basically just write this in front of the radiosity, and where it's like a multiplication by 1. And again, we're summing over J. So the radiosity of the surface I is a constant, so you're not basically not bringing this into the summation. It's just multiplying by a factor of 1. So now we can rewrite all of this and get a fourth expression for Q sub I. Okay, so now we've rewritten this in terms of the radiosity of the surface I and then the radiosity of the other surfaces in the enclosure. And then, just for completion, we'll write down, we know that the net radiation leaving a single surface is equal to the sum of the net radiation exchange between that surface and all the other surfaces. So that's also equal to just the summation of the net radiation exchange between one surface and all the other surfaces. And that's a concept we introduced when we were first talking about black body radiation exchange. Okay, we're pretty close. So now we have multiple expressions for Q sub I, and we're going to use the last two that we developed, numbers 3 and 4, to set up this idea of the radiation network. And again, use the idea of circuit networks for analyzing radiation exchange. So from our expressions 3 and 4, they're both equal to Q sub I. So we can set them equal to each other. So this is expression 3. And then expression 4, and we're going to rewrite it just slightly so that it looks more like a thermal resistance. So now we have our radiosities in the numerator, the driving potential for the heat transfer, and then in the denominator, the resistance, so the V factor in the area. Again, we just brought these down, raised them to the power of -1. So now we have two different expressions for the driving potentials, two different driving potentials between some flux and the radiosity at the surface I. And they're equal to each other. So this makes a little more sense, I think, if you draw it out. So we're going to have basically this node, J sub I, and there's going to be heat transfer going into and out of it. So from this equation, the driving potential is the difference between the emissivity of the surface if it were a black body, so EBI, and then the radiosity at that surface. And then we have Q sub I going in. That's the heat transfer rate. And then the resistance is going to be this quantity in terms of the emissivity. So again, you can think of it as if it were a black body, the emissivity would be 1 and the resistance would be 0. So it would be emitting the maximum amount possible. But because the surface is not a black body, there's some resistance to the radiation, so it's not emitting as much radiation as possible, and you have this finite quantity here, the resistance. So now, on this side, we have the sum of the radiation exchange with all of the different surfaces. So that ends up being this kind of parallel type circuit. We'll say ... So then you have over here the radiosities J sub j summing up over j, so J sub 1, J sub 2, all the way until J sub n, so n the number of surfaces. And then here we have our net radiation exchange between the surface of interest and surface 1, between the surface of interest and surface 2, surface of interest and surface n. And so that kind of makes sense with how like parallel circuits work, right? So you have the total current, the total heat transfer rate flowing in from the left, and then it's equal to the sum of these different heat transfer rates between all of the different surfaces. And then we'll have some resistance on this side as well, and that's going to be 1 over A sub I F I1 for this resistor, 1 over A sub I F I2, and 1 over A sub I F I N. So the way this works is if you have an enclosure that has multiple surfaces, you can basically write up this expression, or write up the circuit and then the resulting expressions for each of the different surfaces. So considering surface 1 as I, surface 2 as I, surface 3 as I, and you are eventually left with a system of N equations and N unknowns. So looking back at these expressions, that's assuming we can calculate the view factor, we know the emissivity and the emissive power, and then we're just left with the radiosities of surfaces I and J for each of the surfaces. So that's N equations and N unknowns. And you can basically solve that system, probably numerically, for the radiosities, and then plug it back in, and you know the heat transfer rate. Okay, so that's kind of the most complex setup for this problem. The last thing we'll consider, and I don't think we'll get to it today, but we'll finish it on Friday. It's pretty quick and just shows how we basically get back to our original radiation expression. But we'll just consider a two-surface enclosure, and that simplifies the problem a little bit. And we can basically show that these expressions simplify down to the original expression for radiation heat transfer that we had. Okay, any questions? Yeah.
Is that all we'll be doing on Friday?
So Friday we'll do that. We will do the course evaluation. And then if there are particular problems or topics you want me to talk about, I can cover those as well. I think I won't give any additional lecture since we didn't quite get through this. We'll just finish this up. Okay, thanks.